Welcome to this product presentation on an overview of Integral CFD++, which introduces its unique and powerful capabilities for complex modeling in various application areas including aerospace, automotive, industrial, and environmental. So what is CFD++? CFD++ is Metacomp's fluid dynamics software suite. CFD++ seamlessly handles most flow regimes on all grid types. CFD++ simulates physics for external and internal flows, including advanced models capable of treating complex physics. There are an extensive set of unique capabilities for moving meshes. CFD++ offers realizable physical, numerical, and mathematical models. The software suite is general, but can be tailored for very specific application areas. CFD++ offers fast computation of steady and unsteady flows with efficient scalability to thousands of CPU cores. The software is used by over 200 discerning organizations worldwide and is running on hundreds of thousands of CPUs at any given moment. Why CFD++? What sets CFD++ apart from other flow solvers? CFD++ is the only commercial flow solver that provides efficient flow solution for any flow regime without sacrificing accuracy and robustness. CFD++ consistently outperforms other commercial solvers in blind benchmarks and workshops. Our software support is unparalleled in the industry. Our customers have direct access to senior support staff members with very fast turnaround times for support cases. Our development activities are customer-driven, such that we are always adding new features to satisfy our customers' needs. We have recently introduced an easy-to-use advanced user interface, the AUI, that is built upon the premise of simplifying complexities. Simulations involving multi-physics and multiple phases are set in a matter of minutes. CFD++ was designed on the principles of unified grid, unified physics, and unified computing. The unified grid framework unifies the treatment of different cell shapes and grid topologies so that the flow solver becomes equally applicable to all cell topologies, including hexahedral, tetrahedral, and recently the polyhedral cell type. CFD++ has the ability to handle all grid types, including structured, unstructured, and hybrid meshes. CFD++ goes well beyond the conventional concept of grid transparency with its ability to handle arbitrary, non-aligned, or overset meshes. CFD++ can handle very large grids efficiently. The unified physics treatment provides the flexibility to solve many types of flows, enabling the same computational framework to handle flows from incompressible through to hypersonic. CFD++ can handle conjugate heat transfer, reacting flows, turbulent flows, moving meshes, multiphase flows, compressible liquids, and non-equilibrium flows. All CFD++ packages can be used to solve both steady and unsteady flows and laminar and turbulent flows, and include the full unified grid and solution capability. Our customers can, however, choose additional packages to find the modules needed for their applications. The unified computing capability allows total portability between different computing platforms, including multi-CPU machines. Platforms supported include all Linux x86-64 compatible platforms and Windows x86-64 compatible. Interconnects supported include GigE and 10GigE, InfiniBand, and proprietary interconnects including Cray and MPT from SGI. CFD++ scales well to very large number of cores. The scalability improvements are universally applicable to all modern HPC platforms. The input-output and initial processing improvements are enabling technologies for using very large number of cores, from hundreds to thousands of cores. Inter-CPU connectivity algorithms have been speeded up by a factor of 10 to 100. Integral CFD++ is part of Metacomp's Integral Computational Multiphysics framework. ICMP is designed with common interfaces and features for mesh generation, CFD, structural analysis, and solution visualization. ICMP offers consistent user interfaces and functionalities between all products. An intuitive and simple guided problem setup process provides a powerful and user-friendly interface at the same time. Let's take a look at the Integral CFD++ AUI. The AUI is comprised of a number of panels which can be rearranged, docked, or undocked. In the default layout shown here, the menu bar is shown at the top left, with drop-down menus for file and tools-based options. Immediately below the menu bar is the toolbar, containing shortcuts to useful view control and save options. The notebook pages feature tabbed entries for each active type of simulation or activity. In this case, a page has been opened in the notebook for CFD++. The canvas area is shown at the bottom right. Users of previous generations of Metacomp software will be familiar with the mouse controls for zoom, translation, and rotation here. To the left, in the CFD++ notebook page is the action tree, which shows a list of completed and yet to be completed items. You'll notice that completed actions are assigned a green checkmark, and yet to be completed actions are assigned a red cross. To the right of the action tree in the CFD++ notebook are the boundary families and cell groups trees. Each boundary family display can be toggled on or off via the small red mesh buttons, and assigned boundary conditions are again indicated by a green checkmark. Note that the colored font for each boundary family matches that of the boundary surface drawn in the canvas. The action tree navigates the user through the problem setup. For each required action item, an action panel appears to the left. These action panels need to be completed or accepted to achieve the required green checkmark in the action tree. At the foot of each action panel is the option to revert to default settings or accept the above settings via the OK button. The action panel options in the AUI are dependency-based. A thinking engine adapts the action tree items based on the user selections. In this example, the initial setup is shown on the left, with various action items for problem definition, physics models, boundary conditions, and output options. Activating the grid motion feature in CFD++ opens up additional action items on the action tree, such as grid motion specification and overall grid motion control. The user can quickly see which panels require the additional settings, and hence you can never miss a step during a problem setup. The boundary families tree shows which families have conditions applied. The green check marks show the BCs that have conditions applied, and the red crosses show the BCs where conditions are not applied. In the boundary conditions tree, you can hover the cursor over the BC for a summary of the applied condition. We'll now go into more details on the capabilities and various models in CFD++. Various topography parameter-free models are used to capture turbulent flow features. All Metacomp developed in-house turbulence models are topography parameter-independent models, which are particularly useful for simulations with moving surfaces. CFD++ also includes many turbulence models from the literature. The RT and SA one-equation models are available, including the QCR and RC variants of the SA model. In two-equation models, several models are available in CFD++, including the realizable K-epsilon model, the nonlinear cubic K-epsilon model, the SST model, and the nonlinear Helston model. The three-equation realizable K-epsilon RT model, the four-equation Langtree-Mentor transition model, and the seven-equation nonlinear RSTM model are all included in CFD++. All these models can be either integrated directly to the wall or combined with a sophisticated wall function treatment that models the effects of compressibility, pressure gradient, and heat transfer. The advanced wall functions in CFD++ can handle any Y+, and provide consistent solutions at any Y+. CFD++ offers seamless switching between low and high Reynolds number approaches depending on Y+. For LES and hybrid RANS LES simulations, several models are available in CFD++, including LNS, DES97, DDES, and IDDES, which is improved delayed DES. There is improved accuracy with smart subgrid scale modeling and large eddy stimulation for automatic eddy seeding in LES. A study of the aerodynamic degradation of an iced airfoil is shown. The flow was simulated using several RANS models at a range of angles of attack. All RANS models underpredict lift in the store region of the iced airfoil. Unsteady simulations were then performed using IDDES on an extruded wing section. We obtain excellent comparisons to experiment using IDDES in the store region at 4, 5, and 6 degrees alpha. The animation shows isosurfaces of the lambda-2 criterion, showing the vortex cores over the airfoil and showing flow recirculation behind the ice shape. CFD++ includes advanced numerics to ensure accuracy and reliability of computations. Density and pressure-based solvers are available for appropriate regimes. A multidimensional, higher-order TVD interpolation is used to avoid spurious numerical oscillations. Approximate Riemann solvers are used to guarantee correct signal propagation for the inviscid flow terms. The preconditioning algorithm, which prevents eigenvalue spread, achieves near-optimal minimum levels of dissipation in low-speed flows. Advanced convergence acceleration techniques include unique preconditioning, relaxation, and multigrid algorithms. For reacting flows, we have a generalized Arrhenius chemistry model with a built-in database with species properties of gases and liquids. Chemical reactions are handled accurately and efficiently using a smart integrator which automatically calculates the number of steps needed for a proper inversion of chemistry. A Chemkin tool enables conversion of species and reactions information from Chemkin to CFD++. A user-defined chemistry feature allows you to program your own finite rate chemistry. Automatic detection and handling of non-integer power reactions are possible in CFD++. Example simulations with reacting flows include combustion cases and detonation waves. A dynamically thickened flame model resolves flame fronts and captures turbulence chemistry interactions for premixed and non-premixed turbulent combustion. In certain conditions, reactions can be both pressure and temperature dependent. CFD++ offers several approaches to model pressure-dependent reactions. Users can employ an ignition source in order to ignite cold premixed solutions, and supercritical combustion can be modeled via cubic equations of state. For conjugate heat transfer, CFD++ can handle isotropic and constant properties as well as composites and variable properties such as temperature-dependent properties. Two radiation models are available in CFD++, the P1 radiation model and the discrete ordinates DO model. In the DO model, the angular space is discretized and radiative heat transfer is solved in each element. An example is shown of the airflow and heat transfer inside a car cabin using the DO model. Temperature contours are displayed on the cabin walls, and radiation intensity is shown on the seat and headrest. The contours show the solar intensity entering at a 45-degree angle through the car window. CFD++ has many useful features to simulate moving meshes with complex geometries including bodies in relative motion. Simulations can be performed using sliding and overset meshes. An accurate treatment of conservation is used for such meshes. We utilize a sequential cutting approach which can solve multiple steps of cutting and blanking, providing a very versatile method for handling lots of different problems. Global and body frame motion modes can be invoked, and CFD++ includes an integrated rigid body dynamics capability with a 6-degree of freedom module. Co-simulation is possible in the 6DOF infrastructure. CFD++ employs an accurate treatment of flux conservation, including mass, momentum, and energy. Examples of moving mesh simulation include rotating machinery and store separation. In mesh morphing, an RBF-based mesh morphing capability is available via tool and solver. Two modes are available: a file-based mode, where the grid motion is specified via file, and a BC-based mode, which can directly apply motion to particular boundary families, enabling easier setup of mesh morphing cases. Special analytical morphing modes are available for flexible disks and pistons. The grid motion files invoke automatic periodicity of motion, and a multi-CPU mesh morphing algorithm is available via tool and solver. Various examples of mesh morphing are shown here, including flap deflection, ice secretion on an airfoil leading edge, and 3D wing deflection. Moving now to multiphase flows. Several models can be used to simulate multiphase flows in CFD++, starting with the Eulerian dispersed phase model, which couples the dispersed phase with the continuous phase. Additional quantities can be tracked for the dispersed phase, such as number density and melting fraction. Various source terms can be computed for the dispersed phase, including lift force, virtual mass, and turbulence dispersion. Melting, solidification, and particle radiation can be modeled. The Grace model can be used for air bubbles when bubbles begin to deform and become elliptical. The oxygen transfer model can simulate oxygen mass transfer between bubbles and liquids. 3 evaporation models are available in CFD++. 2 condensation models are available. and additional models for special physics, such as a secondary aero breakup model and a wall impingement model for SLDs. Going into further details on the breakup model, this model simulates secondary breakup of droplets and has been applied to liquid fuel injection and aircraft icing simulations. This example shows a liquid jet in supersonic cross-flow modeled without the breakup model on the left and with the breakup model on the right. Predicted jet penetration heights are compared with experimental correlations, and we can see an improved prediction with the breakup model active. The breakup model also alleviates the need to guess an initial droplet size for large enough droplets. The wall impingement model for supercooled large droplets simulates droplet wall interactions, including the effects of droplet rebound and splash. The SLD model is applicable to droplet sizes greater than 50 microns. SLD modeling can significantly improve prediction of the collection efficiency, which is an important parameter in computing ice accretion. This example shows a NACA airfoil with leading-edge ice. We compute the collection efficiency for a case with large droplets. On the graph, the blue line shows the result without the SLD model. The red line shows the result with the SLD model. We obtained very good predictions on the lower and upper surfaces of the airfoil and improved predictions at the leading edge in the region of the ice shape with the SLD model. Moving to the Lagrangian dispersed phase model, several primary and secondary breakup models are available with the LDP. The example on the right shows diesel fuel injected into air at varying densities. The case is simulated using LDP with the CAB breakup model. The predicted jet length compares well to experimental results, shown below. We can see the reduction in the jet length as air density is increased. Special physics that can be handled with the LDP include multiple parcel injections and coaxial and cross-stream flows. A spray angle can be specified, as well as variable parcel velocity. The effect of the spray angle is displayed in the two images on the lower left, which show the front view of a jet without and with a spray angle of 90 degrees. The homogeneous mixture model for multiphase flows is a simpler model which solves one additional equation for the volume fraction. In this model, the relative motion between the phases is precluded. Small droplets and bubbles can be handled by the model. Evaporation, condensation, and cavitation can be modeled. A non-homogeneous version of the model, which accounts for slip velocity between the phases, is available. The effect of turbulence dispersion can be included in the drift velocity. CFD++ includes 3 Rayleigh-Plesset type cavitation models. Secondary phase compressibility and material density overrides can be modeled with cavitation. This example shows the cavitation region over a 45-degree cone in a water tank. The volume fraction shows the extent of the cavitation region. The cavitation length L/D is compared to experiment, 12.5 from experiment and 11.5 from CFD++. The volume of fluid model in CFD++ can be used to simulate distinct non-mixed phases, such as a gas-liquid interface, and artificial compression can be used to model sharper interfaces. Surface tension effects can be modeled, and there is a special gravity wave inflow BC to prescribe a wave at an air-water interface. A wetting angle definition can account for wall adhesion. The VOF model has been applied to sloshing and ditching cases and boat flows. The example below shows the free surface flow around a naval boat model. Numerical prediction of the wave profile compares well with the experiment, as shown on the right. This concludes the multiphase flow features in CFD++. A non-Newtonian capability enables the modeling of shear thickening and shear thinning fluids. Several non-Newtonian viscosity models can be invoked. The example shows the velocity profiles in a fully developed channel flow using the Hershey-Bulkley model for 3 different sets of model parameters to simulate Newtonian flow, shear thinning, and shear thickening flow. Velocity profiles with changing viscosity all compare well to analytic solutions. An extensive set of physics source term models are available in CFD++ for modeling swirl, porous media, mass injection. We have a stator blade and rotor model. The solution on the lower right shows the flow around a helicopter model using a rotor model source terms. There are specific models for different flow control devices, such as the jet doublet for active flow control, plasma actuators, and a vortex-like source. The synthetic jet doublet solution on the right displays the use of active flow control to achieve attached flow over an airfoil with flow separation. A user-linked subroutine feature enables you to program your own source term models. For hypersonics and reentry, CFD++ includes a two-temperature model for thermal non-equilibrium flow and also Tannehill curve fits for equilibrium air. An ionized air viscosity model can be used for improved accuracy of viscosity and thermal conductivity at higher temperatures. Species properties for reentry simulations are available over a 5-temperature range up to 30,000 Kelvin, including carbon dioxide for Mars' atmosphere and various carbon and hydrogen molecules, atoms, and ions for ablation. Several catalytic and ablative wall conditions can be applied. These models have been applied to reentry flows, high-speed heat transfer, and scramjets. CFD++ has been extensively validated for a vast array of flow regimes and applications. Detailed validation documents over a range of topics are available from Metacomp, including external and internal aerodynamics, low and high-speed heat transfer, turbomachinery, combustion, icing, and flow control. For documentation, a new user manual is available with Integral CFD++, including in-depth theory and user guides. Each training example now has an overview and video tutorial to walk the user through every step of the problem setup, and there are a range of cases illustrating a variety of flow scenarios. In summary, Integral CFD++ is part of the ICMP framework and is Metacomp's computational fluid dynamics software suite, offering unique capabilities for complex physics modeling, advanced turbulence, and numerics. CFD++ enables fast and efficient computation of steady and unsteady flows and has been validated over a range of flows and applications. The CFD++ framework is general, extensible, and specializable to suit your needs. CFD++ is the right choice for all your CFD applications. For more information on CFD++ and other Metacomp products, please contact us at info@metacomptech.com or visit our website at www.metacomptech.com. Thank you.